So this video is just to do a very quick review of polar functions, what they are, how we graph them, both by hand and on the calculator, and how to switch between polar and rectangular and parametric forms. Uh, so first off, polar functions are a way of graphing on a coordinate plane, and we can still graph in terms of an x and y axis. Uh, in rectangular form, just kind of remind you, rectangular form, we move only at right angles. So we move horizontally, we move vertically. So if I were finding the coordinates of this point in rectangular form, we talk in terms of horizontal movement and vertical movement, x and y. So this would be moving 4 right and 4 up, which would give us the coordinates of 4, 4, making a nice right triangle here. Polar functions are a bit different in that instead of talking about moving horizontally and vertically, we go directly from the origin to a point. And what we care about then is the distance away from the origin and then the angle from the positive x-axis going counterclockwise. So it's just another way of getting to the same place. So here, if I wanted to get to 4, 4, that distance, and we do our coordinates in terms of r, then theta, that distance would be 4 radical 2 for the r, and the angle would be pi over 4 radians. So here, if I'm thinking in terms of, here I have polar coordinates. So if I think, oh, radius is 4, the r is 4, so I'm 4 away from the origin, but an angle of pi over 2, that would be right here. And in terms of x and y coordinates, that would be 0, 4 in rectangular. Negative 3 pi. So I'm negative 3 away, so pi would take me around to here, but then I'm going 3 the opposite direction. And so that would actually be the same as 3, 0 in rectangular. 16, then 5 pi over 6. So 5 pi over 6 is over this way, going here, and going 16 units. Well, this is 5 pi over 6 gives me a reference angle of 30 degrees, and then I would have a special right triangle of 30, 60, 90. So if this is 16, this would be 8, this would be 8 radical 3, but because it's going to the left, that would be a negative, so our coordinates would be negative 8 radical 3, 8 in rectangular coordinates. And then if I had negative radical 2, negative pi over 4, well, negative pi over 4 is going this way. But negative radical 2 means I actually go negative radical 2 this way, up into quadrant 2. And that makes a 45-45 right triangle, or isosceles right triangle, which means that would be at negative 1, 1 in rectangular coordinates. In terms of graphing polar functions rather than just polar coordinates, kind of some basic ones here. If we just are told the radius, r equals 2, that means our angle can be anything we want. So if I measured angle of 0, a point would be here. If the angle were pi over 2, it would be here. If it were 3 pi over 4, it'd be here. If it were pi, it'd be here. If it were pi over 2, it'd be here. And I can just keep going around, and no matter what angle I have to be 2 away from the origin, which gives us a circle. And it would be a circle starting at 2, 0 in rectangular coordinates going counterclockwise. Similarly, if I had r equals negative 2, well, if I have an angle of 0, it's 2 in the other direction. Angle of pi over 2, it's 2 in the other direction. Angle of pi is 2 in the other direction, and I actually, again, end up with a circle. However, this would start at the positive 2 and go this way. This would actually go that way. So it's just a matter of which way we're going around this circle. If I were to see something like my angle is pi over 6, what that means is that no matter what distance away I am from the origin, this angle from the positive x-axis must be pi over 6. So if I have positive r values, it can just keep going out infinitely along that ray. Negative r values just go the other way, and I actually end up with a line. These can be graphed on your calculator just when you go to Graph Entry Edit under Menu. So it's Menu, Graph Entry Edit, Polar, and you can graph different functions. So you get rose petals, you get lemniscens or a cardioid if that were just a dimple instead of a loop. We can get circles as well. If you're really interested in kind of seeing all those different shapes, it's on pages 562 to 563. However, you're not required to know all of those shapes. Just real quick, making conversions. Polar to rectangular, rectangular to polar. If you know what r is, you can get your rectangular by saying x is equal to whatever r is times cosine theta. Y is whatever r is times sine of theta. But then because we can make right triangles, x squared plus y squared must equal r squared. And the tangent of theta would be x divided by y, which actually I have that backwards. That's y divided by x. Whoops. Because r sine theta over r cosine theta, the r's would cancel, leaving sine over cosine, which is tangent. If you're interested in a quick review of how this is done in terms of taking and changing a polar function into a rectangular function, if I had r equals 4 sine theta, I could multiply each side by r, which would give me r squared equals 4r sine theta. Well, r squared equals x squared plus y squared. And r sine theta is y. So then I can move everything to one side. And I'm leaving a blank on purpose because x squared is already a perfect square, but I need this to be a perfect squared as well. So I'm going to complete the square. And if I add 4 here, and then on the other side of the equation, this is now a perfect square. I'd have x squared plus y minus 2 squared equals 4. So I actually end up with a circle of radius 2 centered at 0, 2.